These two men want to create revolutionary products, like thread that is stronger than steel, or smartphones that could cost $10.
Getting the handle of this?
They are among a growing number of researchers and entrepreneurs trying to harness the extraordinary properties of microscopic nanoparticles to remake many of our most important products and the very way we manufacture them. In the heart of New England mill country, where old abandoned factories once turned out spools of thread and bolts of cloth, a new kind of fabric, like black cotton candy, floats out of hot furnaces in Merrimack, New Hampshire, where Nanocomp Technologies is located.
Coming along, Roger?
This large factory floor is the domain of co-founder Peter Antoinette.
Looking good.
Thanks.
Super. More for the customers.
He's a nanotechnology entrepreneur who's built Nanocomp's business on the extraordinary properties of tiny carbon nanotubes.
Anything running well today?
There are trillions upon trillions of nanotubes swirling and binding together in this furnace. And Nanocomp is turning this gauze-like stuff into amazingly strong materials.
What we're looking at here is really nanotechnology for the first time turned into bulk products, yarns, high-strength fibers. And these fibers can be turned to ultra-strong tethers and cables. So why do you care? How'd you like to replace chain with this?
Nanocomp's products include this trash bag-looking material that's thinner than a sheet of paper, but stronger than a speeding bullet. So it's a no-brainer for bulletproof vests.
We've put our material into a vest to make it thinner and lighter. And as I peel it back, and then in here you can see our black sheet material added to it, and there's a bullet right there.
And that's not all the material can do.
The biggest application is to replace the flooring in aircraft. So that sheet is turned into this super lightweight honeycomb. This will actually save weight and fuel, save CO2 emissions with lighter, stronger material.
But what gives nanotubes such special properties? With the diameter of DNA, you need a powerful microscope just to see individual tubes. Magnified over 200,000 times, they're still so mysterious. A model is the best way to explain them.
Carbon nanotube is made of carbon atoms in this unique hexagonal structure that gives them tremendous amount of strength. It's a hollow tube, all right? That means it's incredibly lightweight.
Several sports equipment companies are mixing nanotubes into plastics to make composite materials that are stronger, lighter, and more durable. But Nanocomp wanted to make entire products out of nanotubes. So they had to find a way to get these clouds of wispy tendrils to stick together on their own. The answer was to make the super thin nanotubes longer, so they had many more points of contact.
They're attractive forces, almost like magnetism, that hold the tubes to each other. They cross over, they entangle. They're holding themselves together.
And that is the key to their strength. Nanocomp designed its production process for maximum safety. The clouds of tiny tubes are sealed within a carefully controlled air handling system, engineered to protect workers and the environment. This is 21st century manufacturing in a 19th century New England mill town. Something that makes Peter Antoinette very proud.
You wouldn't normally think that this type of technology would pop up in New Hampshire. It goes to show you that innovation and the idea has to start first. And New England has had a huge tradition of manufacturing from the textile mills, and maybe we're going to be the new textile mill world with our materials.
In the atomic world of nanotubes and other nanomaterials, there's a property that not even Nanocomp has begun to exploit. They are excellent conductors of electricity. As consumer demand for smarter, bendable, even wearable electronics increases, companies everywhere are developing smaller, more flexible sensors and microchips to run them. So if someone could figure out how to replace conventional chip materials with super tiny nanomaterials, they'd have a surefire winner. And this man believes he can do just that. He's Ahmed Busnaina, director of Northeastern University's Center for High-rate Nanomanufacturing. The center was launched with funding from the National Science Foundation to help translate lab-based nanoscience into practical applications, a concept Ahmed wants his graduate students to embrace.
The last experiment that I have done was the paclitaxel drug, which is an anti-cancer drug, which is highly...
Before he began teaching, Ahmed worked with the computer chip industry, where the seed of an idea began to grow.
More than 10 years ago, I started thinking that we need a new technology to get the benefit from nanotechnology and nanomaterials. And the current semiconductor manufacturing cannot do that. I started thinking about a new manufacturing concept, completely new.
A traditional chip factory needs to be highly automated and cleaner than an operating room to prevent contamination. To make a chip, metals and other materials need to be deposited, etched away, redeposited, and re-etched to create the circuitry. The process requires vast amounts of water, chemicals, and gases. The semiconducting wafers are all made of crystalline silicon. Everything here is big, energy-intensive, and costly.
For one chip, you could have 300 to 400 processes.
So Ahmed designed a system that could make chips more efficiently and far less expensively.
Danny, do you need to put a wafer here to teach the robot, or you already got that position?
He's called his invention NanoOps, for nanoscale offset printing system. But what does offset printing have to do with chip making?
Printing in the old days was an offset printing. You have a printing plate, you put the ink on it, you print.
Like printing money, something we'd all like to do. And what Ahmed wants to do is print circuits this way. At his Northeastern lab, Ahmed and his team developed a process for turning a typical silicon wafer into a printing plate, or template. They begin by projecting a pre-designed circuit pattern onto a wafer that has been photosensitized. Then, using simple chemistry, they develop the pattern just like a photograph. After a few more steps, the template is ready to become a printing plate. In a fully automated system Ahmed has designed. Here's how the process works. A robotic arm will load the template and blank wafers. The arm takes them to precision alignment stations so they will match up perfectly. The template is sent to an assembly module for the key part of the printing process. The template with its etched circuitry is dipped into a well containing nanotubes or other types of nanomaterials. When an electric current is applied to the well, the nanomaterials are drawn out of the water and adhere to the etched pattern like ink. The newly inked template is aligned to the blank wafer, and both are taken to the transfer module, where a pressure device presses the two together. In an instant, the pattern that was inked on the template is printed onto the wafer. And like a printing press, the process can be repeated to make as many wafers as you want from the same template.
We can use that template thousands of times.
And additional layers of circuitry can be added by inking a new template with a different pattern and pressing it against the existing wafers to make more complex electronics. The entire process takes minutes compared to hours in a traditional chip factory.
The reason we use offset printing because it's a lot faster. You ink the template and you print, and in one shot you're done.
You can print circuits or sensors on cheap, flexible plastic wafers at the macro, micro, and nano scale quickly and accurately. In Ahmed's process, there's no waste.
Because you only use what you want. There's no chemicals that you have to use to etch or to react. And that means that you can use any material you want. You're not stuck on silicon.
In fact, the entire production process consumes fewer resources than a chip factory.
The fact that we don't use vacuum, we don't use high temperature, and we don't use a lot of water. And so as a result, our cost is a fraction. It's less than 1% of what it makes to produce a chip.
The only question is, when it's all put together, will this first-of-its-kind device actually work?
This was a big challenge for us because we never made a tool before. So to bring technologies from the bench-type experiments to this was a big leap for us.
To build his dream machine, Ahmed needed an experienced partner. So he turned to experts in the precision design of robotic devices.
This is going to be for the first time?
Yeah.
Krasy Petkov is an entrepreneur, inventor, and CEO of Malara, an industry leader in precision mechanics. Building the NanoOps machine is an enormous gamble for Malara as well as for Ahmed.
The company invests quite a bit of money. I believe we're close to $500,000 right now. When it's finished, maybe it's going to be more than that. May work, may not, but most likely it's going to work.
Malara is used to taking chances, and they produce some real winners. Like the super smart Talon robot that has detected and eliminated explosive devices in Iraq and Afghanistan.
So the reason we chose Malara is because we needed alignment and registration at the nanoscale. And they already make alignment systems for the semiconductor industry. And they also make robots. So they had all the right ingredients for us to work with.
And their engineers know how to work under pressure. Something that has taken center stage since NanoOps is due to be unveiled to the public in only 4 weeks.
But you need a wafer here to teach it. We're putting in pretty long hours, and we expect to put in more long hours in putting the whole system together and then testing it. On top and bottom. It's going to be very difficult.
The big day has come. Inside Northeastern University's George Costas Research Institute, invitees from academia, industry, and government have come to see Ahmed's invention and assess its worth. Behind the scenes, everyone is nervously prepping for the big moment. Will visitors be impressed enough with NanoOps to invest in it? That's the big question, and the reason everyone here is so anxious.
We're very excited. I mean, we have 160 people coming, 52 companies, and a lot of government agencies. Everybody's pumped up.
I'm very honored to be on the front.
But as Ahmed and Krasy and other speakers prepare the crowd, back in the display area, there is deep concern. The machine has stopped working.
To announce that we will start a new consortium called NanoOps. NanoOps, if you don't know what that means.
No one out front has a clue that a possible tech disaster has just occurred.
It's a cluster tool. It's in the clean room, and we'll start with group 1.
But as the pressure mounts, And as the VIPs, including George Costas, begin lining up to see it, NanoOps swings into action and begins to work perfectly.
Take the template, goes here to the assembly, and then it's aligned. This aligns it at the bottom there, and then it picks it up and takes it to the assembly station. The next one shows.
It's a great moment for Ahmed, Malera, and Northeastern. The years of research and months of high-stakes fabrication have produced a truly impressive debut.
I can just show you here, if you can approach it here. So it starts here. The robot takes the wafer, take it to the aligner.
That's Cihan Yilmaz taking center stage. He's Ahmed's most senior postdoc, who has spent years working on NanoOps.
And for me, it's a very exciting moment because this is the thing that I developed, the technology, some of the technologies, and it's very impressive to see them. It's coming to a product stage.
This is energy versus power density. Graphite is
For all the graduate students, this public forum is an experience they never would have gotten in a classroom or lab.
So here, Ashley is doing measurements. So sometimes.
But this is Ahmed's day. And for him, the measure of success will be this audience's response to what they've seen.
It's very fast.
This machine is so compact.
Which means very small devices. You're not wasting any material.
Which is potentially way, way cheaper than the existing process.
Being able to do this here on our shores is crucial to our security.
It's a way of handling nanoparticles. It's going to make sense to a lot of people.
To have much higher resolution, we take it to Boston campus.
Despite the crowd's obvious enthusiasm, Ahmed is listening for more than praise.
I'd like to hear them say, well, how can we get involved? How can we collaborate? I'd like to hear that one first.
He wants good impressions to become good investments, and for good reason.
But without capital, without funding, doesn't matter.
Lisa, you doing all right? All right. Let's go over this.
It took Peter Antoinette years to build Nanocomp's success. This impressive factory floor is a far cry from his first 500 square foot space.
Hey, Kevin, what do we got?
We wouldn't be here if it hadn't been for a first contract from the Office of Naval Research. We might have been the smallest defense contractor in the United States. And then we had our big breakthrough contract with the Army Natick Soldier Center for body armor. It was literally millions of dollars.
What attracted customers was Nanocomp's ability to move high-strength carbon nanotubes from a lab environment and into a production process for making next-generation materials in volume. And what will attract investors to NanoOps is its potential to bring speed and agility to the production of tiny sensors and flexible electronics, while drawing inspiration from the past.
They are doing some remarkable work in taking one of the oldest industrial technologies, printing, Gutenberg, and being able to print carbon nanotubes and other nanoscale materials in an offset manner to make electronic components. An entirely different, ultra low-cost methodology. You're looking at a revolution.
It will take more time in the lab and in the factory before NanoOps is ready to produce complex commercial electronics. But the machine is already making devices like super tiny plastic sensors with applications from saving energy to saving lives.
And these sensors can do amazing things because, first of all, they can be very, very small. They could be much smaller than a grain of sand.
With nanoscale sensing elements 1,000 times thinner than a human hair, these sensors can detect the earliest signs of infection or disease, for example, and transmit the data wirelessly.
So there's a huge demand for sensors, especially flexible, very inexpensive, that can work for a long time. They can detect viruses, bacteria, they can detect a variety of things. So this opens a whole door.
The buzz in the crowd over nano-ops is certainly a good sign for Ahmed. Many here are already imagining the new possibilities it offers.
We would certainly look towards making some of our sensors.
We're looking to make a new type of solar cell.
For advanced memory applications, integrating them into the soldier's uniform.
I would love to see, like something like the space station.
Good.
Ahmed Busnaina and Peter Antoinette, transforming the very way we make things, pioneering America's future in nano-manufacturing.